So the main idea of foundation models is that, well, let's pre-train on a large time series data set. And then once pre-trained, they work on single time series. So this data set size that I just talked about in the deep learning section is not an issue anymore. I want to point out that global and foundational models are conceptually really the same. So any global model can be used as a foundation model. The difference is really in the way how you evaluate, right? In the global model, you say, I care about all the series I trained with. I myself trained that model. So yeah, I'm going to evaluate on all of that. Whereas in the foundation model, most probably somebody else trained on a large corpus of series that you don't care about. And now you are just evaluating on only your series, which is really only a small subset of all the series that are there, right? So any global model can be used as a foundation model. But the important thing now is that these global model guarantees that I've talked about in the global model section, they do not hold. And we are back to kind of square one, where the series need to be related or relevant in some way for this to work, right? So if you remember, the idea of the global model is the series don't have to be related because you relate them later through the evaluation regime. You are going to evaluate as an average of everything, which means it makes sense for the global model to trade in some accuracy in some series for accuracy somewhere else. But now this is not the case anymore. These series are not related through the evaluation regime. You don't care about Wikipedia web traffic forecasting, right? So you don't care whether this method works well for Wikipedia web traffic forecasting. You only care about your series. So there's no connection anymore. The question is now really how relevant is the training corpus for your use case. Okay, so in terms of architecture, yeah, there are two big groups. Some of these foundation models, they train from scratch. So they all are obviously pre-trained transformers, so GPTs. So they are heavily inspired by, well, and not all of them are transformers, but I think the main idea is, yeah, so like as an LLM is kind of a foundation model for language, let's do the same for forecasting. So they are obviously heavily inspired by these LLM architectures. And so then some of the foundation models, they just use the architectures of LLMs and adapt them for forecasting and then train from scratch with only time series. And then some others say, well, I just use a pre-trained LLM that has been pre-trained on language, and now I either use that directly or I fine-tune it, or do things like that. Yeah. And then, well, if they train on time series, where do the data come from? Well, our repository is always in there. I mean, the first proposals, they leaned heavily on our repository. Now newer, well, now people have found more time series. The repositories have grown, and the data sets are a bit bigger. Yeah, if you use an LLM directly, the question is, well, how can you convert the time series to text so that you can kind of feed it into that LLM? Okay, again, many of the earlier proposals have really not great evaluations. Just as an example, Time LLM, again, in their own evaluation, in the appendix of their own paper, they lose against the most simple methods like versions of naive on M3 quarterly. Then TimesNet, Time Mixer, and many others that adopted the TimesNet evaluation regime, they all claim state-of-the-art performance on the M4, and then you look up the original M4 paper and you see they clearly are not winning by any means. So the original competition winner is a lot better than what they do. but they just left out the original competition participants from their evaluation. And then you ask, why did you do that? And they say, oh, we wanted to benchmark only deep learning methods. And then you say, well, the winner of the M4 was deep learning. That was ESRNN, so recurrent neural network. Well, anyway, I don't want to go too deep into this. I've written a paper about that and a YouTube and a LinkedIn post that you can read if you're interested in this. What's going on there? Yeah, another thing last year in NeurIPS, there was a spotlight paper, are language models actually useful for time series forecasting? And they had as a conclusion, popular LLM-based time series forecasters perform the same or worse than basic LLM-free ablations, yet require orders of magnitude more compute. So yeah, so they basically performed an ablation study that papers like Time LLM probably should have done in the first place, but then obviously they wouldn't have been published. Yeah, so like feeding a series just into an LLM or doing some fine tuning, I've not really seen it work very well anywhere. Okay, but evaluation is certainly getting better, right? So newer models, they evaluate on GIFT-eval. GIFT-eval is a large data set. It contains all of our Monash repository plus some more, 23 data sets with 144,000 time series across 7 domains and 10 frequencies. Yeah, supports prediction tasks ranging short-term, long-term, both univariate and multivariate, and it's on Hugging Face, and new methods routinely submit their forecasts here. Quite nice, but we're going to talk about it in a minute a bit more, because it also has some problems. I wanted to make sure you're aware of them. Okay, which models are in this space? Here I just give you some examples, and well, in this list it's, you know, constantly expanding, so many new proposals, but just to give you an idea of what was out there at the time I record this video. The first foundation model is TimeGPT from Nixla. It's a proprietary model, transformer based. Then we have, for example, Chronos, which is an encoder-decoder transformer that tokenizes the series. Chronos Bolt, that then uses patching and predicts directly future quantile distributions. Chronos 2, that is a quite new proposal at the time of recording that can incorporate external variables. Times FM, that is purely decoder-based transformer. Times FM 2.5, that has fewer parameters and longer context lengths. Moirai from Salesforce, from the people that also host GIFT-eval, is a masked encoder transformer. Then LagLlama, that combines Llama's architecture with time series features. And then, for example, Tiny Time Mixers, that is an MLP-based model, so no transformer, that combines adaptive patching, resolution, prefix tuning, and multi-level channel modeling. Yeah, okay, so that's all nice. And these foundation models, they definitely have many situations where they work well and they come out in short succession. But there are also some quite fundamental problems that I would like to highlight. And well, that obviously goes back to this, what I've told about before. So the global models, the idea is that the average performance is improved at the expense of performance on particular series, right? Okay. And as global and foundation models are the same, now if you have a paper that evaluates very broadly as an average performance across many domains, it is kind of covered by this global model theory, right? So, but then you later use that model for your particular use case, and you don't have these guarantees, right? So now we are back to the idea that these series in training need to be related to your series in testing. And then, well, depending on the data set, you can obviously fine-tune the foundation model, or maybe you are just better off building your own model from scratch, right? You don't really know. You have to try, right? You have to do that yourself. Yeah, because think about it. The idea of the foundation model is to be a generalist model, right? Let's be very generalist. Let's work on everything, and let's evaluate as an average performance across everything. But you are not interested in a generalist model. Like, you are hardly ever going to predict the Bitcoin price together with I don't know, the yearly GDP and your own household's energy consumption, all with the same model, and you are interested in getting a good average performance across that, right? So yeah, exactly. So that's a problem. But don't get me wrong. So these models, they achieve quite competitive results, and usually they don't beat everybody, but they definitely will give you a very good baseline with minimal needed forecasting knowledge, right? If you have no idea about forecasting, you get one of these foundation models, you run it on your data, and you will get something that is reasonable, right? But you need to evaluate that model on your data, on a holdout set, and you need to compare against your own benchmarks that you care about. And very often you will still be able to outperform the foundation model with your kind of bespoke modeling. Yeah, and now, well, maybe to make that a bit more concrete. So let's say you have a single yearly time series, right? Which obviously is not the focus of these foundation models, but nobody told you, right? You just heard Chronos is great for forecasting. Okay, I have a yearly time series. Let's run Chronos on it. So again, you can, the Chronos paper has a long appendix where you have some interesting tables, so you can have a look. So I have here the M1, M3, M4 yearly data, and well, I said I have one yearly time series, right? So I take these yearly data sets that are mixed together quite widely, right? So I don't include tourism yearly because that is a quite homogeneous data set. Okay, and now let's check what works best on this. And now, well, you can't see it very well, but you see there is like a lot of kind of boldface, which means this method is good down here. So we see this method called SCAM performs best on yearly data in this evaluation. Now, what is SCAM? It's a simple combination of univariate models. So basically, it's an ensemble of just auto ETS, auto theta, auto ARIMA, and another ETS implementation. And that performs better than Chronos on yearly data. So if you have yearly data, probably you want to just still stick to the classics. Yeah, and we can do a very similar exercise with gift eval, right? So gift eval is actually dominated by high frequent data, but nobody really usually would tell you. So, and now one problem is that ARIMA and ETS, they do not handle multiple seasonalities, they do not handle long seasonal periods, they are not designed for high frequent data, right? And a second thing that is a problem, they optimize towards the mean of the forecast distribution. That's because internally they do maximum likelihood under Gaussian assumption, which effectively makes them minimize mean square error. But then you look at the gift evaluation, and they use Maze, which actually evaluates for the median of the forecast distribution, and thus for MAE or Maze. So basically, you have two problems here. First one is, if you now say, look, I win on gift eval on average Maze over everything, and AutoArima is like down here, way at the bottom, certainly not competitive. And I would say yes, but you run AutoArima on hourly time series, which is something that nobody would ever do. And you also use an error metric that disadvantages these methods, right? So what if we actually look at data that ARIMA and ETS were designed for, monthly, quarterly, yearly? For example, let's look at monthly data. So this is, I just, earlier this morning, I went on GiftEval and I just said, give me only monthly and sort by best maze. So we see we have here this one that has leakage. This one also has data leakage. So we can exclude these ones. This one, it's interesting, but it's not a foundation model, right? It's machine learning. So would be interesting to discuss, but right now we exclude it. And now we see, okay, AutoArima has 0.75. Okay. And now Chronos 2, 0.756. So Chronos 2 is basically on monthly data, just as AutoArima. The only one that is really kind of better is this one here. I'm not sure what it is, but you see also like very small. And that's just AutoArima, right? I mean, you could easily do just an ensemble of ARIMA and ETS or some other things. I mean, people have come up with a lot of things how to perform better on monthly data than AutoArima with classical methods, right? So yeah, so if you have kind of really these classical problems, monthly, quarterly, yearly, use the traditional benchmarks. Chances are they will be good and outperform foundation models, because foundation models do not really have that focus. They are more geared towards higher frequent data, it seems, right? Just from this leaderboard here, and from if you look at the data that they train with.